Welcome everyone. We're going to get started. So I just want to encourage you to take your seat, as I don't want to take away from our speaker's time. Oh, thank you. That was very effective. Hello, everyone. My name is Petra Deakins, and as the president-elect of Paleoceanography and Paleoclimatology, it's my pleasure to welcome you to the 20th annual Cesare Emiliani lecture. I want to start by thanking the people who nominated your colleagues for this award and also the people who served on the committee to make the selection this year. Before we start, I just want to tell you a little bit, just really briefly, about AGU's Centennial Celebration, which is gearing up. It's actually the official launch is happening Friday afternoon with a session that's the Centennial Plenary, which will be a selection of really prominent scientists giving these really rapid-fire talks about the science that we've accomplished in the last 100 years and sort of a vision of where we could go in the next 100 years. So throughout the year, you're going to see activities. AGU sort of designated different months with different themes, and it turns out April is Paleoclimatology month. So expect to hear from us in April. We plan to do sort of 100 pictures on Instagram. We have some plans and some ideas for Twitter as well. And then Annie Tamilovich, I'm sure I'm mispronouncing her name, is a student, and she and a collection of other students and early career people are working to assemble the 100 seminal papers in paleoclimate. So keep an eye out for communication from her and submit your selection of what you think are the key papers. And I wanted to highlight that because I think it's certainly the foundation of those 100 papers will certainly start with Cesare Emiliani. Then at the fall meeting, we're going to have a couple of special sessions for PP, but there will also be an all-day session for our neighborhood. You know how we all have these blue tags? We're in the earth-covering neighborhood, and so there will be an all-day session around that for each of the neighborhoods. So at this point, it's customary to give a little bit of background about why this lecture series is named after Cesare Emiliani. And some of us have been to all 20 of these. Can't quite believe I'm one of those people, but it appears I am. But it's important to remember that there's people in this room who have never been to AGU. This is their first AGU, and some of those people were at the event last night, and so I want to make sure that we give this background. So Cesare Emiliani was born in Italy in 1922, and he worked there to get his first PhD in micropaleontology, a bit of an overachiever. He moved to Chicago shortly after that and worked with Harold Urey to work on his second PhD, which was in geology, which he got in 1955, after which he went to Miami's Institute of Marine Sciences. Emiliani is considered the father of paleoceanography because during his time in Chicago, he and Urey were the first to solve the problem of how to measure isotopes in foraminifera. And more importantly than that, not only did he learn how to make the measurement, he realized that foraminifera were acting as recorders of climate and oceanographic conditions, and that he could reconstruct temperatures and salinities by using this tool. He, for the first time, showed that ice ages were cyclical, which gave really strong support to the Milankovitch theory, and it really revolutionized the way we think about our ocean and climate history and how things change in our climate. This paper, which you can't see very well, and it appears to be an image of Peter Schwartz's copy of this paper. I don't have my own. It turns out, I looked this up, it is still getting cited an average of about 20 times a year. So this year it's up to 18 citations. And, you know, that's 20 years past his death, so it's that is a foundational paper if ever I saw one. His influence reached well beyond just his papers. He was a big driver in initiating ocean drilling programs. He had a good collegial and collaborative relationship with Nick Shackleton, who of course realized that you could use benthic isotopes to reconstruct ice ages and use that as a tool for chronology. And this is a picture of them at a union session in AGU sometime in the early 90s, according to Larry Peterson, who sent me this picture, at a session honoring Cesare's retirement. So it's now my pleasure to introduce Dr. Jean Lynch Stiglitz, who's our speaker this year. She's a professor at the School of Earth and Atmospheric Sciences at Georgia Institute of Technology. She's a fellow of the AAAS, and she's published over 60 papers in peer-reviewed journals. She's best known for her pioneering work using the benthic isotope foraminifera from a depth transect on either side of the Florida Straits, and realized that she could use that depth transect to reconstruct the density structure of the water column. And then for the first time was able to quantitatively estimate the amount of water flowing through those straits, and then took that tool and applied it to the last glacial maximum to show that the flow of the Gulf Stream was less vigorous during the last glacial maximum compared to today. I certainly think that that's another paper that could go in that list of 100 papers. Annie, I hope you're taking notes. Since that groundbreaking work, she and many of her students, she's had a lot of students and postdocs, have continued to work on furthering develop this really unique technique of using isotope composition of foraminifera to reconstruct water column density structure, and therefore are able to answer questions about deep ocean circulation, the position of the ITCZ in the eastern tropical Pacific during the last glacial maximum, the western boundary flow in the North Atlantic, and a host of other things. So Dr. Lynch Stiglitz is also a leader in the field more broadly. She was a co-PI on a piston coring expedition to the Line Islands, and she's hosted and participated in many workshops and working groups that have really built collaborations among paleoceanographers, but also encouraged collaboration among modelers and paleoclimate data people. So please join me in congratulating Dr. Lynch Stiglitz and all her accomplishments as we look forward to her talk.
All right, well, it's nice to see so many friendly faces in the audience, and I'd first just like to thank the PP and Ocean Sciences sections for inviting me to give this lecture. It's really an honor, and thank the colleagues that nominated me. I'm also going to show some work today that spans it's kind of a best of talk about some of the the approaches we've taken to reconstruct ocean circulation using reconstructions of density in the ocean. And so I'd like to acknowledge the co-authors on all of those talks. Are they? They should be up there, yeah. So I'll try to mention them as they come up, but I may forget. So these are just the co-authors on some of the papers that I'll be talking about today in alphabetical order. Hopefully you find your name on there somewhere. I'd also like to acknowledge the funding agencies, in particular the National Science Foundation, who has funded much of this work over the years. So I'll start by just saying that we've known for quite some time, since the 1970s or so, that there were dramatic changes in the ocean circulation during the last ice age. This is a picture of sea surface temperature as reconstructed from the assemblage of shells of fossil foraminifera that accumulate on the sea floor. And today we get temperate species all the way up into the North Atlantic, reflecting the flow of surface and intermediate waters up into the North Atlantic, providing heat. During the last ice age, those are replaced by polar assemblages. So clearly something was very different with the North Atlantic circulation. Shortly after that, in the 1980s, we started realizing that deep water properties were different in the Atlantic as well. So this is a compilation of carbon isotope measurements in benthic foraminifera. The carbon isotope composition of the foraminifera records biological cycling much in the same way that nutrients do, so the red colors indicate low nutrient water. So today we have, we can see the outflow of North Atlantic deep waters with as a low nutrient water mass, and clearly that was a different situation during the last ice age, with those low nutrient waters confined to the upper 2 kilometers of the ocean. So this this southward flow of deep waters and the northward flow of surfaces in intermediate waters that compensate the deep flows is referred to as the Atlantic meridional overturning circulation. But these tracer reconstructions leave open many possibilities. So we could have just a shallower overturning cell, maybe shallower and stronger, shallower and weaker. We could also have more extensive deep overturning cell coming from the south. So it's important to, and it's also even been suggested that maybe the water mass properties could be accommodated by the same circulation as today with simply different initial process properties. So we need to get other indications about how the Ice Age ocean was circulating. Why do we care about how the Ice Age ocean was circulating? Well, there are a couple of important questions for understanding the climate of the last ice age, which involve ocean circulation. And one of these questions is about the stability of the Atlantic ocean circulation, that overturning circulation during the last ice age. There are some very abrupt climate changes that are seen in the northern hemisphere. This is a record that reflects temperature on Greenland. And the leading hypothesis for the cause of this is that it has to do with changes in the overturning circulation strength. Another key question for quaternary climate is what drives the cycling in carbon dioxide, as observed here from the bubbles in the ice cores. And so it's apparent that the ocean was storing more carbon dioxide in the deep ocean during the Ice Age times. But in order to understand this, we really need to know where is this water coming from, how much is coming from different locations, and what are the active processes at these locations. So what I will do today is I will first just provide some basic background information on how ocean density provides information on ocean circulation. And then I will move into the part that has to do with Emiliani, and that is the reconstruction of past ocean density using oxygen isotopes in benthic and planktonic foraminifera. And I'll start by talking about some work we've done in the subtropical Atlantic, where we can get very good relationships between oxygen isotopes and foraminifera and density. And then I'll finish up by talking about some more recent work that we've done in the cold ocean and talk about what oxygen isotopes in benthic foraminifera, when combined with other proxies for temperature and salinity, could potentially tell us about ocean circulation. So just to start, the upper ocean flows are in what we call a geostrophic balance. The dominant forces are the pressure gradient force, so the tendency of waters to flow from high to low pressure, and that is balanced by the Coriolis term, which acts at 90 degrees to the velocity. So as a consequence, the water tends to flow around the surface topography, so clockwise around the highs in the northern hemisphere and counterclockwise around the lows. So this is a view of the topography of the surface ocean due to these that is associated with ocean circulation. So this is from satellites. And you can see very clearly all of the major circulations, such as the gyres, very clearly outlined by the topography of the sea surface. So if we had a paleo satellite, we'd be all set. We'd just reconstruct this map for the paleo ocean, and we could call it a day. Unfortunately, we have no paleo satellite. So one other thing that probably most of you have observed is that the topography in the sea surface is mirrored in the topography of the picnic line, or sharp contrast in density between the warm upper ocean and the colder, deeper ocean. And if we think about why this is the case, we can think about it if the upper ocean flows are going to diminish with depth, if they're not going to extend all the way to the sea surface, then at some depth, the pressure gradients have to disappear. So here, below the thermocline, we have to have no pressure gradients. And so if the sea surface is higher in the center of this diagram, well, the density better be lower than on either edge if we're going to have the same pressure gradient at both locations, if those pressure gradients are going to disappear at depth. So for the upper ocean, that picnic line is a very nice mirror of that sea surface topography. And again, so here the blue colors are low density at 150 meters. So these are places where the picnic line is deep. And then these yellow colors in the tropics and subtropics are higher density. So those are places where the picnic line, which coincides with the thermocline, is shallow. So we can again see, very nicely outlined the major ocean flows. You can even see the crenulations here associated with the reversing current systems in the tropical Pacific. So if we had some Paleo Argo floats, we'd be all set. But wait, we do have Paleo Argo floats. I'll tell you about those in just a few minutes. And we can get even a little bit more quantitative. This is just a picture from a textbook showing that if you have geostrophic flow, you also have what's called the thermal wind relationship, which says that you can reconstruct the vertical shear in the velocities from the lateral gradients in density. So here we have a classic textbook example of the sharp contrast in density across the Gulf Stream. You take two CTD profiles, one on either side. That can give you the shear in the velocity. And then if you take another piece of information, some sort of constraint, or assume that the velocity goes to zero at some level, you can calculate the flow. And this is the geostrophic method, which has been used for many, many years in physical oceanography. So if we had Paleo CTDs, we could do that, and we'll show some Paleo CTDs in just a few minutes as well. So now I'm going to move on to the part that involves Emiliani, reconstructing ocean density using oxygen isotopes in foraminifera. So the isotopic composition of the calcite that foraminifera are formed from depends on the temperature at which they calcify. This is just a nice recent calibration from Tom Marquito for benthic foraminifera, showing that the difference between the calcite and the seawater oxygen isotope ratio is nicely correlated to temperature. But the O18 of foraminifera will also reflect the oxygen isotopic composition of the seawater in which it's formed. In the warm part of the ocean, so these are global ocean waters that are over 5 degrees C, there's a nice correlation between the oxygen isotopic composition of seawater and salinity, since they're both determined by evaporation and precipitation processes. And it turns out if you look in a very specific area, this relationship is a lot tighter. So this apparent scatter is really a series of different relatively tight relationships in different parts of the world ocean. So the O18 of a foraminifera will increase at colder temperatures and for higher salinities. Well, those are the same two factors that will increase the density of seawater. And so here is just, again, for all of the waters in the world ocean greater than 5 degrees C, the relationship between density and the O18 of calcite. And again, there seems to be some scatter here, but it's really a series of different, much tighter lines for different regions of the ocean. So back to our Paleo Argo floats. So we want to, if we want to see a map like this, from the past ocean, so this is, remember, the density at about 150 meters water depth, then we need some little Argo floats. So what we have is we have planktonic foraminifera that tend to calcify at different layers in the ocean. So some of them are, have symbionts and calcify right near the surface, but some of them tend to calcify much deeper down. So for example, Globirotalia tumida or Globirotalia truncatulinoides. And so these two species in particular have been very useful in reconstructing the depth of the pycnocline, and so are really serving as these little paleo Argo floats. So I'm just going to, because we have some samples in the western North Atlantic where I'm going to show our benthic work, I'm going to show some reconstructions of thermocline depth using the oxygen isotopic composition in truncatulinoides. This is actually work that was done a long time ago by Allegra Legrand as part of her master's thesis before she entered the model world. And so here what I'm showing is the oxygen isotopic the predicted isotopic composition of calcite that formed at about 350 meters water depth in the Atlantic. And again, you can see the circulation reflected in that distribution. Here, I'm showing at sites where we have core top data, what that modern data looks like, just to better compare to the core tops, and these are the core tops themselves. So I know for those of you in the back, you can't see very well, but it does a pretty good job of approximating conditions at about 350 meters. Well, we weren't the first to figure this out. Other people have used this approach, and actually the first person to use this approach was Emiliani himself. This, I believe, is the first paper he ever published. It's called Depth Habitats of Some Species of Pelagic Foraminifera as Indicated by Oxygen Isotope Ratios. So, and he established that truncatulinoides calcified at about 220 meters water depth and was one of the deeper calcifiers. So I'm going to show you some data from the western subtropical Atlantic. So I just want to talk briefly about circulation in this area. We have the wind-driven subtropical gyre. But we also have this western boundary current is augmented by some flow that comes from the South Atlantic as part of the surface return flow associated with that overturning, the meridional overturning circulation. And we also have an augmentation of the Gulf Stream with these recirculations further north. So if we zoom in and look at the modern core top temperature, these red colors are indicating a relatively deep pycnocline, and the bluer colors are indicating a shallower pycnocline. And so we can see that tilt in the pycnocline associated with the strong western boundary current. And when Allegra did the same thing for the last glacial maximum, she found a virtually identical pattern. So this gives us confidence that the basic outline of circulation during the last ice age was very similar, with the Gulf Stream separating at more or less the same latitude, with the western boundary current flowing through the Florida Straits as it does today. So we're going to now zoom in to the Florida Straits. And the Florida Straits has about 30 spheredrops of water flowing through, and about 13 of those 30 spheredrops is associated with the return flow of the meridional overturning circulation, and the rest is associated with the wind-driven flow. So if we look at a cross-section of density across the Florida Straits here between the Florida Keys and Cuba, you can see on the Florida side that we have much denser waters at the same water depth than we have on the other side. And this is the density contrast associated with the shear in the Gulf Stream as it moves through the Florida Straits. So we're going to build some Paleo CTDs on either side of the Florida current to compute some geostrophic velocities. And we did this. This is Bill Curry and I had a coring cruise, and we collected a bunch of cores at different water depths on both the Florida side of the current and also on the Bahamas side of the current. So the way we build our Paleo CTD is we take sediment cores at different depths, and then we can analyze the oxygen isotope ratio at the top of these cores, and that will give you our recent density at those depths, and then we work our way down core to build profiles for density during the past. So this is just near the top of the core, the recent oxygen isotope ratio in foraminifera. So the symbols with the lower values are on the warmer Bahamas side, and the colder, denser waters on the Florida side are in the blue symbols. And the lines that are underlying the symbols are the predicted values from modern water column conditions. So we can convert those to density and calculate the geostrophic transport. So today the current is small near the bottom, so we apply a level of no motion at the bottom and calculate about 30 spherogyps of transport. And both the amount and the vertical structure agree very well with modern observations. So we actually have nice data going back about 8,000 years for all of these cores, or most of them. And so this is Paleo, so we're going backwards in time as we move to the right. So this is 8,000 years ago. And so from 8,000 years ago to the present, we have fairly steady flows, but a gradual increase of a couple of spherogyps or so towards the present. So what can change the Florida current on these long time scales? So as I mentioned before, we have wind-driven flow, and so changes in the amount of that wind-driven flow going through can change the strength of the current. In that particular paper, we felt that that was the most likely explanation for that subtle rise over the last 8,000 years. But we also can have changes in the Atlantic meridional overturning circulation, which contribute to the transport through the Florida Straits as well. On very short time scales, so on monthly time scales or annual time scales, we don't necessarily expect a change in meridional overturning circulation to match the change in Florida Straits transport in a straightforward way. But we have to remember that on these longer time scales, we're looking really at a series of steady circulations. And so the processes that we have to think about are a little bit different from, for example, the processes that are active in interpreting the data from the rapid array. So one way to check that we're thinking about this correctly is to look in models. And what I'm showing here is some results from the model simulations that were started by Zhengyu Liu several years ago. So these are the SynTrace simulations where coupled ocean atmosphere GCM was run from the last glacial maximum to the present. And they are now running this simulation, the same scenario with a tracer-enabled ocean model. So this model includes many paleoceanographic tracers, but it now includes oxygen isotopes as well. So this is a nice way to check, does the contrast in 018 of calcite across the Florida Straits reflect the density contrast? Well, here the dark line is the 018 contrast, and the pink line is the density contrast. So I should say this goes from 20,000 years ago to 12,000 years ago. So this is a time where we have strong changes in the overturning circulation. And we can also check whether the contrast in density reflects the flow through the Florida Straits. So here, the kind of purpley line here, or blue, or whatever color it is the flow through the Florida Straits. So it matches very well the density contrast and the 018 contrast. And then we can also see how well does the flow through the Florida Straits on these timescales match the changes in the Atlantic meridional overturning circulation. Well, that's shown in red right here. And that's showing, at least for this model, the changes in wind-driven flow are very small compared to the impact of changes in AMOC on Florida current transport. So that gives us more confidence as we go back in time and interpret the changes that we see. So this is just looking at one of these abrupt climate changes. This is the Younger Dryas, the most recent of these abrupt climate changes that occurred on the deglaciation. So this was a return to cold conditions. And here, as we go further back in time, we lose those shallower cores, but we still have the deeper cores. And so for the modern, those deeper cores do show that contrast with the less dense water on the Bahamas side, the more dense water on the Florida side. But when we go back into the Younger Dryas, that density, that the O18 contrast is much reduced. And so we interpret that as a weaker density gradient, weaker shear in the Florida Straits, and less transport. And this is consistent with multiple lines of evidence from other tracers for a weaker AMOC in response to a meltwater routing event during the Younger Dryas. We can extend this approach further back in time. So here are two sediment cores, one on either side of the straits. So the blue is on the Florida side and the red is on the Bahamas side. So we have a nice large gradient today. That gradient disappears during the Younger Dryas. And we can see that that's accompanied by lower O18 values on the Florida side. So if we think about that, the tilt of those isotherms, those strongly tilted isotherms flattening out, that leads to less dense waters at this particular water depth on the Florida side, and these waters should be warmer as well. And what I'm showing here is some recent work that my graduate student Shannon Valley is doing in collaboration with Tom Marquito, showing that indeed there is a warming during this time, that this low O18 is driven by a warming, as we expect from a flattening out of those density surfaces. If we go further back, we see another excursion towards low O18 and warmer temperatures during Heinrich Stadial 1, suggesting a flattening out of the isopycnals, a weakening of the AMOC during Heinrich Stadial 1 as well. But as we go back to the glacial, we don't really see much change in the density contrast across the straits associated with Heinrich Stadials 1 and 2. And in the paper that we published in 2014, we suggest that maybe if the AMOC was already very weak and perhaps a little bit different during this time, that that meltwater associated with those two Heinrich events was not able to do much to the transport in the Florida Straits and perhaps even the AMOC. So going back to some of these key questions that I put out at the beginning, one was about what causes the abrupt climate changes. And what we found is Atlantic overturning circulation can respond to the input of fresh water into the Atlantic, so kind of confirming hypotheses about what's going on in the Younger Dryas and during Heinrich Stadial 1, but doesn't always do so. Okay, so moving on to the deeper parts of the ocean and the colder parts of the ocean, let's think about what oxygen isotopes and benthic foraminifera can tell us about the past density surfaces. Well, it gets a lot more complicated in the colder part of the ocean, and one of the reasons is that when sea ice forms, it will fractionate salinity by quite a bit, but it doesn't fractionate the oxygen isotopes by very much. So if you have sea ice forming in some place and being exported and melting someplace else, that will cause higher salinity in one place, lower salinity in the other place, but it won't do a whole lot to the O18. The other complication is at very cold temperatures, density of seawater doesn't respond to temperature changes very much. It's really controlled by salinity. So in the warm surface ocean, like I've been talking about previously, stratification is really set by temperature, whereas in the very coldest parts of the ocean, and it is increasingly set by salinity, and of course the ocean was even colder during the last ice age. So with that caveat, I'm going to show some results that we have that are mostly in the upper ocean at 30 degrees south, but do extend into the deeper parts of the ocean. And these are basically what we're doing is looking at the density contrast across the entire ocean basin at 30 degrees south. And so here, instead of just looking at the shear of the velocity in a single current, we're looking at the shear associated with the entire surface to deep overturning of the Atlantic meridian overturning circulation cell. So this shear is associated with denser waters on the eastern margin. It's the opposite of what we had in the northern hemisphere because of the change of sign in the Coriolis force. But you can see the density contrast associated with this overturning circulation. So if the overturning circulation changed in the past, so these are simulations from the PMIP, last glacial maximum simulations, which suggest a strengthening of the overturning circulation. Well, this shear would also strengthen, and we should see a larger density contrast across 30 degrees south. So again, we're going to use our Paleo CTDs. We're going to take sediment cores, or we did take sediment cores from a variety of water depths. This is just showing that in this region today, the relationship between the O18 and the foraminifera and the density is fairly straightforward, and importantly is the same on both sides of the South Atlantic. So here are the holocene values plotted on top of the predicted modern values, and the signal is much smaller than what we see in the Florida Straits, but you do see that on the eastern, on the western side where we have less dense waters, we have lower O18, and on the eastern side, in red, where we have denser waters, we have higher O18. If we go back to the last ice age, so again, if we had a stronger circulation or even a shallower AMOC of the same strength, we would expect the contrast between the blues and the reds to be even stronger. But what you see is it actually, if anything, goes in the opposite direction. So the most straightforward interpretation of this data is that you have a very weak AMOC, or even an AMOC that might be in the opposite sense during the last ice age. However, if you don't like this result, and a lot of people for various reasons don't like it, it apparently contradicts some other proxies out there, you could argue legitimately that how do we really know that the relationship between density and O18 on both sides of the Atlantic was still the same during the last ice age? And again, we also have that colder ocean. We could have sea ice playing a larger role than it does today in this region. So the final example that I'll show you is a reconstruction of across the Antarctic circumpolar current. So again, we have a very strong current that's associated with a very strong shear. The current is much stronger at the top than it is at the bottom, so we have a strong density contrast across the Antarctic circumpolar current. So again, we have sediment cores as well, some of them to the south of the ACC, or some of them to the south of major parts, but not all of the ACC. And we also have a transect of sediment cores from north of the ACC. These are mostly from south of Australia. So these blue dots are the modern oxygen isotope ratio across the ACC. So the open dots are from the Antarctic margin with higher O18, higher higher density waters, and then the blue dots from the south of Australia with lower density waters. But here we are truly getting into the cold ocean, and we don't dare simply interpret these 018 values as seawater density. So what we did in this study is we used other proxies to try to establish the temperature and salinity, and thus the density of the major water masses in this region. So examples, magnesium, calcium from planktonic foraminifera, constrained surface water values, form assemblage data, magnesium, calcium in benthic foraminifera. We also pore water data was very important because it provided constraints on the lower circumpolar deep water end member. And so what we did in this study is we simply used the 018 as to interpolate between these end member values that were estimated using these other proxies. Well, when we do this, there are a lot of uncertainties that go into those estimates of the temperature and salinity, and a lot of uncertainties that go to a lot of other assumptions that we threw into this estimate. And so there is the bottom line is that what we calculated was an enhanced transport, but considering the errors, it really could allow for a very wide range in last glacial maximum ACC transports, from reductions to doubling of the current value. And but it is interesting to notice that the 018 contrast is also stronger during the last glacial maximum. So it is recording the sense of what we calculated using these other proxies. We also did some uncertainty analysis, and it's actually not too hard to make this a lot better. Right? We need better estimates, in particular, of Antarctic intermediate water properties. That would really, really help. And also more, and so that could be done for temperature using foraminifera proxies. But for salinity, we really need the only good proxy for salinity that we appear to have right now are pore water reconstructions. So to get more accurate values, we really need to be doing more pore waters. And I'm encouraged that it seems that there are some efforts underway to get some more information from pore waters. And I should say that our South Atlantic cross-basin transport could also really benefit. We could try to quantify things a lot more with that if we had pore water information from either side of that 30 degrees south transect in the South Atlantic. So moving back to the second key question about climate during the last ice age, what is the cause of the CO2 cycles, with the caveats about needing more direct TNS measurements. All of the results, the reduction in the ACC and the reduction in the shear of the overturning at 30 degrees south are consistent with more water, deep water sourced in the Southern Ocean and less northern source deep waters. And so this would imply the need to have a more efficient Southern Ocean carbon pump in order to account for those low CO2 values. So just to summarize, I hope I've convinced you that paleogeostrophic approaches have provided a very strong constraint on ocean circulation in the North Atlantic subtropics and the upper branch of the Atlantic meridional overturning circulation. And in particular, the 018 and planktonic foraminifera could be applied in many, many places to look at upper ocean current. So I would, if you're out there taking sediment cores and doing isotopic measurements on foraminifera, look at the oxygen isotope gradients and see what they have to say about the ocean currents in that region. To do the Paleo CTD approach, right, it requires an island or some, a strait like we had in the Florida Straits, but there are other places that you could potentially do that. And then the other thing is that in order to really get deep water circulation, we really need to improve our estimates of deep water density and the relationship between deep water density and O18. And I think pore waters are the best way to go about that, at least from our currently available proxies. That's all.
We have time for questions.
Great talk. So, question, one of the obvious places that your geostrophic technique work is sort of in the swamp that was in Madagascar.
Yeah.
You or anybody else who done reconstruction to get a sense of what's happening on the Indo-Pacific side of the...
Yeah. Yeah, there are no existing, benthic isotope measurements at the right, or sediment cores at the right water depth. So, we would have to go out and get some sediment cores. That's kind of always been something that I said, I'd like to do that someday, but somebody else should do it because, I may not get to it. But yeah, that would be a perfect place. And, it also has a boundary current, but it's also another one of these boundary current that at least today is associated with the return route of the global meridional overturning circulation kind of goes through that area. So, yeah. Yeah, somebody should do the Kuroshio too.
No other questions? No more questions? It was all, that's how good the talk was. Oh, there's one more.
So I think you saw the farthest back in time was that the plot I showed with the various Heinrich stadials, and that is as far back in time as the Florida current core goes. So it's a very dynamic region, and based on the cores we took, we're not optimistic that you can go much further back without running into hiatuses. And in some of the other cores, that's the only core where we're able to go that far back in time because the other cores did run into hiatuses.
Okay, well, let's thank her one more time for the great talk, and here's her